Hello, I'll give a walkthrough of understanding graphs and message passing in this collab. So, this notebook starts by importing NumPy, Matplot library, Network X, PyTorch, and utility libraries. Network A is used to create visualized graphs, while PyTorch is used later for implementing trainable GCN models. Next, let's go for graph examples. This cell visualizes different types of graphs. The goal is to show that the graph data is made of nodes and edges. For example, in a social network, peoples are nodes and the edges are relationship. This is very different from regular table data because relationships are part of the data. Next, we'll go for adjacency matrix. And here the notebook demonstrates an adjacency matrix. If two nodes are connected, the matrix entry is 1. Yeah, here we can see the matrix entry is 1. If the two nodes are not connected, then it is 0. So this is one of the most common way to represent graph structure mathematically. Next, we'll go for representation comparison. This cell compares graph representation like edge list and adjacency matrix. And edge lists are memory efficient for sparse graphs, while adjacency matrices are easier for matrix operation. This matters because GNNs often use matrix multiplication. Next, we'll go for a graph class with node features. And here we create a simple graph class. It stores the number of nodes, edges, adjacency, matrix, and node features. Node features are important because GNN do not only use connections, they also learn from attributes of each node. Next, let's go for permutation problem. And this in a permutation problem explains why normal machine learning struggles with graphs. If we reorder the nodes, the matrix changes, even though the graph structure is still the same. GNNs are useful because they are designed to handle this kind of permutation issues. Next, let's go for message passing. And this section introduces the main idea of GNN's message passing. Each node collects information from its neighbor and updates its own representation. With one layer, a node learns from immediate neighbors. With two layers, it learns from neighbors or neighbors of neighbors. Next, let's go for normalized adjacency. These are all the previous neighbors of neighbors and all the explanation. And okay, I forgot to explain one here, which is a normalized adjacency, which where if we see the normal adjacency, here and all we can see that the cell computes the normalized adjacency matrix used in GCNs. Self loops are added, so each keeps its own information. Normalization usually prevents high degree nodes from dominating the whole aggregation. So after saying this, let's go for GCN from scratch using NumPy. Here we implement a GCN layer from scratch. The formula is basically normalized adjacency multiplied by node features and learnable weights. Then the full NumPy features and then the full NumPy GCN is trained on a small node classification task. This section is useful because it shows the math clearly before using PyTorch. Next, let's go for PyTorch GCN. Yeah. So now the same GCN idea is implemented using PyTorch here. PyTorch makes training easier because it handles gradients automatically. The model learns node labels by using both node features and graph connections. So after this, let's go for Karate Club demo. These are all training the PyTorch, and this we can see that the graphs, if epochs, these are like how many epochs and how much loss and train accuracy and test accuracy we got. These are the three respective graphs we can see, and upon these three graphs we can see the final test accuracy turned out to be 1. Next, so node classification on real data. This is what I was trying to say. Like I have considered a we have considered here a Karate Club demo. This final demo applies GCN to Zachari's Karate Club graph. Um, so Yeah, here we can see. So, which is a classical social network data set. What your model does is it tries to classify communities in the network. Here also we can see, like, bordered, which are bordered or are trained models, and we can also see the results, which is correct or mostly almost 33 out of 34, and misclassified notes are 8, and the final test accuracy is almost 96.43. So the main takeaway in this GNNs are powerful when relationship between entities are important. So that's it with this demo. That's it with this collab walkthrough. Thank you.